When you heat or cool things, not only will their length change, but their area and volume changes as well. In this video, we're going to find out how to calculate changes in area when you heat things up or when you cool them down. Imagine you have a gold plate sitting on your table with all your other gold stuff, and let's imagine it's a perfect square. So it has a length L, so its length is L, and the temperature of that plate right now, let's call it as T. Well, you heat it up. That's what you do. You heat up that plate and you see the whole thing expanding. So here's what you see. The whole thing expands, and as it does, carefully see that its length has expanded over here and over here as well. In both sides the length has expanded, and therefore there's an extra area. The area has expanded, the area has increased. Let's keep that over here. So let's say right now the new temperature is T plus delta T. T plus delta T. And its new length, well, that would be the old length L plus some extra length delta L. Some extra length delta L. And the same story on this side will be L plus delta L over here. And now the big question is, how much has the area changed? That's what we need to figure out. So how do we do this? Well, we already know how to take care of changes in length. We have seen previously that the change in the length during thermal expansion or contraction can be written as delta L equals alpha L. Alpha L is the linear expansion coefficient times L times delta T. We've talked a lot about this expression in previous videos, and so if you're not familiar with this, or maybe you need a refresher or something, it'd be a great idea to go back, watch those videos first, and then come back over here. So we know how to take care of length and changes in length. So the question now is how to calculate the change in area. Well, all we need to do is ask ourselves, how do you get area from length? Hey, that's easy. For square, the area is just the side squared, right? So let's write that down. So the area initially, that would be L squared. Side squared is L squared. This is the initial area. What would be the final area? Well, the final area, let's call it as A dash. That would be the final side squared, right? So final side length squared. So what's the side length now? Well, it is L plus delta L. So it would be L plus delta L, the whole squared. And now to calculate the change in the length, we just have to subtract these two. So the change in the area, we'll write that over here. That's going to be the final area, which is over here, L plus delta L, the whole squared, minus the initial area, and that is just L squared. And at this point, I want you to pause the video and see where the algebra takes you. Just go with the flow and see if you can do something. Just see what expression you end up with. All right, let's do it. So what can we do next? Well, we have an a plus b whole square form. Let's expand that. It'll be a squared plus b squared plus 2ab. So if you expand this, you'll get a squared plus b squared plus 2ab minus L squared. And notice this cancels. And so we end up with 2L delta L plus delta L whole squared. That is our change in area. And at this point, we may say, okay, there's nothing more to do, right? But there is one more step we can do over here. Well, we need to remind ourselves that delta L is an extremely small quantity. Check it out over here. We've seen this before also, that when things expand, delta L is much smaller than L. So what can you say about L delta L and delta L squared? Let's compare them. Can you see that L delta L is going to be a much larger quantity compared to delta L squared? Let me give you an example. Let's say L is something like 100. Then delta L would be something like 0.1. So in that case, 100 times 0.1, well, this term, forget about the 2. I'm just caring about this term. That would be just 10. Well, this would be 0.1 squared. That would be 0.01. Now, 10 plus 0.01, can we approximately say it's almost 10? We can do that, right? If we don't want exact result, we just want approximations. So in this case, just to simplify this, we can just forget about this. So we could forget about this, and we can just forget about this, right? So we can neglect delta L square because it's much smaller compared to L delta L. All right, let's do that. Okay, so we will neglect this term. So this term is neglected. So neglect this. And so what we now end up with is delta A equals 2L times delta L. But what is delta L? Ooh, we already know that. And you might be wondering, well, isn't this only applicable for wires and rods? No, it's applicable for any object. 2D, 3D, any kind of object. Even over here, we can apply this. So we could just say, well, we already know how to calculate delta L. Delta L would be alpha L times L times delta T. Oh, this is getting interesting. Now let's see what we end up with. We end up with, let me just put a division over here. All right. So what we end up with is we get 2 alpha L, let's write that first, 2 alpha L times L squared. Oh, what's L squared? Oh, that's the area, that's the initial area. So that's just A times delta T. And let's go ahead and box this because I think we have simplified this as much as possible. And now just see what we have done. We have now figured out the change in the area. So if we know what the initial area is, and we know what the change in temperature is, and if we know the alpha L of a material, then we can calculate delta A. We don't need anything more. So just by knowing this, we can figure this out. But can you see the similarity between this expression and this expression? They are very analogous to each other. Just like how you have change in length equals some number times length, original length times delta T, you have change in area equals some new number, some new constant, times area times delta T. So just like how alpha L is the linear expansion coefficient, tells you how much length has expanded, this 2 alpha L, we can now call that as the area expansion coefficient. And we often write this as alpha A, and we call this as the area expansion, getting a little crowded over here, coefficient. So just like how alpha L helps us calculate changes in length, alpha A helps us calculate changes in area. And if in any numerical they ask you to calculate the change in area and alpha is not given to you and only alpha L is given to you, you can still do it because alpha A is just 2 times alpha L. But one thing we need to remember though is that we arrived at this expression by assuming by neglecting delta L squared, and we can only do that when delta L is very small compared to L. In other words, this whole thing is an approximate relationship which works when the expansions are very tiny. And one last thing which you can check for yourself is that alpha A should have exactly the same units as alpha L because it's just 2 times alpha L, right? So 2 has no units, so it have the same units. Kelvin inverse would be the units of alpha A. Now you may wonder that we derived this expression and we got this result for a perfect square plate, but would it work for any other shapes? The answer is yes, and you can try and do it yourself for shapes like say a rectangle or a circular plate. Try them, it will be a great exercise, but it turns out that in general, if you take any shape, even 3D for that matter, and you calculate the changes in the area due to changes in temperature, you end up with the same expression, you end up with exactly the same result as long as you're dealing with very tiny changes.